So again, in theory, this is review from Physics 11, but again, I'll teach it as though you're learning it from scratch. I'll just go a little quicker. Colin's smiling because this looks an awful lot like the lessons I gave you guys last year. Yeah, I kind of changed the numbers, but I use the same approach. Friction. Friction, it turns out, is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. Even things that appear smooth, if you zoom in to the microscopic level, they end up being bumpy. So your desks, for example, your lab tables might feel quite smooth, but if you were to zoom in, you would see that actually they're very bumpy and the stuff on top of them is very bumpy. And the bumpier it is, the bigger the force of friction will be. Friction resists sliding. As such, it can resist motion, like when you're trying to slide something. It can also create motion, such as for walking or rolling. Example 1. It says, draw the direction of friction in each case. Draw the direction of friction in each case. So if we're sliding a block along the ground and the block is moving to the right, which way would the force of friction be acting? Friction will be acting that way. What about for a car speeding up? Now, I have a lot of people that say to me, a lot of people tell me that, okay, grade 12s, if you need a photo retake, you can get one, but if you want to wait till the end of the lesson, that would help as well, okay? A lot of people tell me that a motor is what makes a car go forwards, and I'm telling you, a motor can't be what makes a car go forwards. Otherwise, when you start your car in the morning and it's in neutral, is the motor running? But is the car moving forwards? Then it's not the motor. Because I think it's that obvious. What makes a car go forwards? Well, for a car speeding up, if you follow the wheels, it looks like the wheels are actually exerting a force backwards against the ground. Now Newton's third law kicks in, the one that says forces come in pairs. If your tires push backwards against the ground, what will the ground do? Push forwards against the tires. What force is that? Now, this is not a normal force, because a normal force is straight up. This is parallel to the ground. Hey, that is friction. Friction can create motion, not just resist motion. And then for a car slowing down, when you tap the brakes, Jake, what you're actually doing is you're causing your tires to exert a force forwards against the ground. Newton's third law, forces come in pairs, will kick in. If the tires exert a force forwards against the ground, what will the ground do? Exert a force backwards. What force is that? I'm telling you, it's friction. And this tie explains why it's tough to drive on snow or ice. On snow and ice, is friction bigger or smaller or the same size as on regular pavement? Smaller. See, it's nothing to, the tires are still there, the motor is still there. What has changed? The fact that now friction can't be as big, you might be demanding more than friction can exert. And if you do, and friction can't be that big, now Newton's first will kick in. You have an unbalanced force, the car is going to accelerate off the road. Oops, car crash. The amount of friction, it depends on two things. The first, it depends on the type of surfaces that are in contact. Ice on ice, not much friction. Sandpaper on sandpaper, rougher surface, way more friction. We give this stickiness, this resistance to sliding, a name. We call it the coefficient of friction. We have a symbol for it, the Greek letter mu. This letter. There's your coefficient of friction. It has no units, it's a dimensionless quality. Later on I'll show you why that's the case. But mu is not measured in newtons, or it's just a number. It's usually a decimal. The bigger the decimal, the stickier the objects are to each other. So if mu is large, there's lots of friction. If mu is small, there's not much. For example, steel on ice has a mu of about 0.01. Rubber on concrete has a mu of about 0.75. Can you have a mu bigger than 1? Yep. Glue can hold its own weight plus other. Or, in fact, dragster tires have mu's bigger than 1 because we just mentioned what force pushes a car forwards? Friction. How can you increase friction? Well, one way is stickier tires. That's why they do a smoke show before a drag race. It's not because they want to impress the crowd. They're melting the rubber. Hey, what's stickier, melted rubber or non-melted rubber? They increase their coefficient of friction. It means the dragster will accelerate more. It's good physics. So friction depends on how sticky the objects are. The other thing it depends on is the force pushing surfaces together. Now, last year, that force was almost always gravity, but gravity is not accurate. What really is, thank you, sir, what really is a good example of the force sticking objects together is the normal force. The normal force. And I'll convince you of that why in a second, Jordan. But this is why we have said, if you want to go down to the box, we say this. Friction is how sticky the objects are, mu times the normal force. It is not mu mg. It ended up being that a lot last year, Tice, but that's because we gave you basic questions. If I say to you, what's friction, I want to hear mu times the normal force. I don't want to hear mu mg. I'll freak. What's friction? It's mu times the normal force. How do I calculate friction, Justin? Mu times the normal force. Let me convince you of that. Example 2, it says, consider the block below, which is being pushed by student 1 across a rough surface at a constant speed. You know what? I would underline the word constant speed. What does constant speed tell us? That tells us that A equals, right? Suddenly, student 2 pushes down on the block with a force F. You know what? Let's put it into context. How many of you have ever slid the benches in the gym across the gym floor? Okay, so I'll go with Quinn since he read. Quinn, you're pushing the bench along the floor and you're going at a constant speed, and then Isaac, your idiot friend, decides to come running and jump and land on the bench. What's going to happen? I got to disagree with you. The bench's mass doesn't change. First of all, since you're at a constant speed, you'll probably come to a stop. Yes? Yes. Why? Well, initially, if A equals 0, we have F applied equals friction. Balanced. You okay with that? Yeah. Okay. Well, if he pushes down here, well, let's answer the question. It says this. If student number 1 maintains a constant applied force, what happens? Let's call this A, B, C, and D. What happens to the weight? Now remember, weight equals mg. When Isaac jumps on the bench, does the mass of the bench change? So does the weight of the bench change? What about the normal force? So are you okay with right here the normal force equals mg because we're not sinking into the ground like quicksand, we're not flying in like Superman? Now look at the second situation. What are the forces acting on this? Get the obvious one. Yeah, can we get that without the hesitation? Right? Get the obvious one. Okay. But do you notice with Isaac pushing down, there's another force pushing down? See it right here, the extra push? So that means, is the bench sinking into the ground like quicksand? Say no. Is it flying into the air like Superman? Okay, so the vertical forces have to be balanced. Now the normal force is going to be, because it's got to cancel out gravity and Isaac. So we haven't changed the mass of the bench, because that's all we're looking at. The mass of the bench hasn't changed. It's just that Isaac is applying another outside force. So what happened to the normal force? Increases. So what happens to the force of friction? Well, if friction is mu times the normal force, and the normal force just got bigger, what happens to friction? Now, initially, Quinn, you were pushing at a constant speed, which means that your applied force was exactly equal to the force of friction initially. If friction just got bigger, you know what? Now your applied force isn't big enough to overcome friction. What's the bench going to do? Come to a? It says explain your answer. There. I think we just did. But I figured a vertical list would be easier to read than filling it in there. Hey, remember I mentioned when we were going over the homework, it's the idea of dominoes. Once the first thing falls into place, there. As soon as we said the weight doesn't change, something else had to change. Normal force. Okay? So we calculate friction as follows. Friction is what times what? Mu times the normal force. Friction is what times what? Mu times the normal force. Friction is what times what, Lewis? I never want to hear you say mu-mg, because this year it almost always won't be. It won't be. Last year, Jake, yeah, I didn't add extra. I didn't have people sitting on the bench in our example. This year, all the time. Or, you know what else Isaac could do, Quint? What if you're pushing and pushing and pushing and you can't move it? How could Isaac help? He could lift up a little bit. What would that do? Would that change the mass of the bench? No. What force would that change if he lifted up? What would happen to the normal force if he lifted up? Well, now the normal force wouldn't have to be as big. So what's going to happen to the force of friction? Okay? And you may have noticed this if you've ever tried to move furniture, slide something heavy. Here's a table here. If I'm dumb and I want to slide it, I'll push down. Yeah. Now, I was pushing this way too, but by pushing down, did I change the mass of the table? What did I change? Normal force had to get bigger to cancel out me pushing down. Okay? Now, if I pull straight, I got to pull with 3 fingers to overcome friction. But if I'm really smart, I'll lift up as I pull. I have 1 finger I could have pulled. Did the mass of this change? No. What changed? I reduced the normal force.
Excuse this final interruption. Any students who have not yet gone down for photo retakes or
if you need your retakes, go get them, although I'd like to think I'm better.
Please do so now. This is last call. Thank you. Room 1004.
Here's a little thought experiment. Hey, I see 4 answers to pick from. You know what? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So example 3, it says, a student gives an old shopping cart a big push on a flat, rough surface. You know what? Let's think parking lot, but a paved one that's really bumpy and lousy, and a shopping cart. Which of the following is the best force, the best free body diagram for the cart, keyword, after the student has released it? So what we're talking about is this. Now this is smooth, but here's the shopping cart. We're not talking about while he pushes it. We're talking about, look. Right there. Okay? While it was rolling. What are the forces acting on the cart? A, B, C, or D? Who says A? Got to be A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Who says B? 1, 2, 2.5. Who says C? Who says D? Okay, I'm going to give you 30 seconds. Convince your neighbor that you're right. Talk it out. If there's a group of 3, Sophia, or you can talk to Riley. What do you guys think? Okay, bring it back. Convince me. What's the correct answer? People say A, people say B. Convince me. Which of these must be wrong? Why does C have to be wrong? I agree. Why? So if there's no horizontal forces, if the net force is 0, now Newton's first kicks in. Can it be slowing down? Say no. Because Newton's first says if there's no net force, you have to be going in a straight line at a steady speed. Right? This would be outer space. It would just keep going forever and ever and ever like in outer space. We're not used to that here on the Earth because friction is all around us, but I'm telling you, based on that diagram, this object wouldn't stop. Which way would D be accelerating? Is he speeding up? I don't think that's happening. So convince me, A or B. Dev. Wait a minute, it's going forwards. How can there be no force forwards? This is just like last class when we threw something straight up and some of you said, well, it's on its way up. Shouldn't there be a force pointing up? No. All the forces are pointing down because it is slowing down. Okay? It says, explain your answer using principles of physics. C and D are impossible. Constant speed or speeding up. A, since net force is slowing down. Can't spell decelerating properly. Okay. And again, I hope, Lewis, I'm starting to convince you a good free body diagram. In fact, honestly, if I gave you this question and you just redrew the free body diagram and labeled everything, I'd take that with no English. If you just said, look, hey, what are the forces acting on this cart? Quinn, get the obvious one. So I have gravity. What's the arrow pointing up? What's that? Is this cart sinking into the ground like quicksand? Is it flying into there like Superman? This is what allows us to deduce there must be a normal force. Hey, what's this force pointing to the left? It'll wait. Okay? That's the right free body. That's the correct free body diagram. So, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, and then find the acceleration. You know what? There's 2 questions. I'll divide my page in 2. And I'm going to do these simultaneously in that I'm going to do a free body... Well, wait a minute. Jake, did they give me a picture of each block? Then rather than do a separate free body diagram, well, you know what? I'll do a free body diagram beside them in this case. I think I will, just so you can see it. So here's one. Here's the other one. Let's do the left-hand one first. Hey, Ty, what are the forces acting on this block? Get the obvious one. Gravity. I agree. MG. Ty, is this block sinking to the ground like quicksand? Is it flying into the air like Superman? So there must be a balancing force, and it's going to be exactly the same size as gravity. What force will I call that? Because it's normally there. Actually, what else? Look at the picture. What else did they give me? Look at the picture. What else did they give me? Find the thing that has newtons next to it in the picture. What else did they give me? 20 newtons. What do we call that outside force? Do you remember what I gave it a name? Quinn's not on his phone or anything foolish like that because his physics is more important, right? Yeah, let's call it F applied. Just so that both our diagrams look identical. So Ty, which way is this block moving to the, accelerating to the? So which way will friction be acting? Am I going to draw friction bigger, smaller, or the same size as F applied? Smaller, because you told me it's accelerating to the. So the winner must be to the. So I'm going to go like that. Let's do the right-hand one. What are the forces acting on this block? Get the obvious one. Gravity. What else? Before I do the normal force, look at the picture. What else is there in our vertical direction in this picture? Do you see it? So I'm going to, next to the mg, put a little 15 newtons there. And then I'm going to say, is this block sinking into the ground like quicksand? Is it flying into there like Superman? So the vertical force must cancel out both of the downwards forces. Do you agree? Normal force is definitely bigger than mg. Is that okay? Okay. Let's keep going, Jake. What else? I totally agree. 20 to the right. I'll call that F applied. What else? Which way? And I deliberately drew this friction arrow a little longer than this one because I'm pretty sure friction is bigger. Why? Because the normal force is bigger and friction is mu times the normal force. In fact, we may find out that friction is so big that this won't move. Okay. It says write a vertical force equation. What are the forces down in the left-hand diagram? mg. What are the forces up? Since we know everything's balanced, I think I can say this, Lewis. Stay green, stay blue, Mr. Duke. Everything down equals everything up. What about on the right-hand side? So on the left-hand side, the normal force equals mg, gravity. What about on the right-hand side? What does the normal force equal? mg plus 15. Cool. B says find the force of friction. Well, friction is what times what? Friction equals mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? So now I can say it's going to be mu mg. What's mu? I don't know. What's mu with you? No, what's mu? 0.12? What's m? What's g? Okay. How big is the force of friction? You know what? I should be able to do this in my head. It's going to be 10 times 9.98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8. It's going to be 11.76. Yeah? Wait a minute. How many sig figs is that? Let's go to 3 sig figs since it's an answer. Units, friction. Force of friction does have units. Mu has no units, but what about the force of friction? Newtons. B. They want me to find the force of friction. Friction is what times what, Lewis? It's on the box on the previous page. Friction is what times what? Friction is what times what, folks? Help them out. Lewis, friction is what times... Look up, Lewis. Friction is what times what? Ready? We're going to do that again. Friction is what times what? So mu times the normal force. I don't know the normal force. Oh, but look. I know another forces the same size as the normal force. What forces are the same size as the normal force? So it's going to be mu, and then I guess I'll put it in brackets because it's that whole thing. Right? It's going to be 0.12 10 times 9.8 plus 15. Can I do this one on my head? Let me see. 10 times 9.8 is 98 plus 15 is 108 is 113. 0.12 times 113 is going to be 11.3 plus 2.26. So it's going to be 13.3. 13.56? Or am I off?
No, that's it.
I am? I can do math in my head. How many sig figs is that, Rob? Units, it's a force. Newtons. Is that okay, Faizan?
Yeah, but what's just the last friction?
Wouldn't it just be the what?
The last friction from the first
No. No, 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 no. Friction is what times what?
mu times 1 friction.
So, mu. What's the normal force? What's the normal force? You got to do the whole replacement. No, you can't just add it on in here. That's totally different. That would be giving you a friction force of like 20, well, you add 15, that 20 is way bigger. That's not, no, 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 no. Because this force here also gets multiplied by mu. Not a one-to-one relationship. Is that okay? Good question. Hey, let's keep going. Faizan, let's keep going. It says write a horizontal force equation. See my free body diagram? See. Who's winning?
The applied force.
Who's losing?
The friction.
So my equation's going to be winner minus loser equals MA. Hey, Faizan, let's do the right-hand one. Look at the picture. It's in front of you. Who's winning?
The applied force.
Who's losing? Are you telling me it's the same equation? It is the same equation here. It's just that what we've changed is going to be the magnitude of the force of friction. Find the acceleration, it says. Okay. Okay. Well, Quinn, here's the acceleration, right? I'm coming back to you because this actually goes full circle to the question you asked me at the beginning of class. Quinn, see the A? Right there? How would I get the A by itself? Divide what? Okay. Yeah, but by the way, don't ever say divide it, because too many, I still have kids say, oh, you'll divide the A. No, I don't want the A on the bottom. I want to leave it. So divide. Okay, so if I hear you correctly, I think I do, you're saying this would drop down. This would drop down, and you're saying just divide by M? You'd be correct. Hey, what was the applied force? You got to look at your picture, because I've scrolled down. What was the applied force? 20? Minus, what was friction? Now you should be scanning part A, part B, part C as well, right? Because maybe we calculated it. I think we did we not? We're on the left-hand side. What would I use, 11.8? I don't think so. Which one would I use to be more accurate? I'll use 11.76, my accurate one, right, Quinn? What was the mass? There you go. Crunch that, please. I should be able to do this in my head. It's going to be 20, take away 11 is 9, take away 0.7 is 8.3, take away 0.6 is 8.24 divided by 0.824? Double check me. Is it?
Yep.
Is that 3 sig figs? I'm okay with that then. Acceleration units. By the way, if you're not trying to do these on your calculator, you should be following along, because hopefully you've clued in you need brackets around the top. Yes? If you're getting the wrong answer, make sure you ask. What are units for acceleration? Quinn, I think we're going to do the same thing for part... Oh, first of all, I put a part D over here. Let's make that part C. For part D on the right-hand side, I think I'm going to end up with the acceleration equals the applied force minus friction all over M. It's going to be, was it still 20? Or did I change the applied force in the right-hand side? Is it minus 13.6? No, don't use 13.6, Mr. Dewick. Use 13.56 over 10. I should be able to do this one in my head. 20 take away 13 is 7, take away 0.5 is 6.5, take away 6.44, 0.644? Double check me.
Yep.
I like the right-hand question. I like the right-hand question. I like the right-hand question. Except, Jordan, I would not walk you through all the steps. I would just give you the right-hand side, and I would say find the acceleration. And I would expect you to clue in that you need to do a free body diagram, that you need to find the normal force, that friction is mu times the normal force. I don't know the normal force. Look, 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 another force same size as the normal force, and walk through it. Okay? Now, let's, going all the way back now to Isaac jumping on the chair. What if Isaac pushed down harder? What if this 15 got bigger? Right here. That would make what? The normal force bigger. Yes? Which would make friction bigger, smaller, or the same size? Which would make the acceleration, if this got bigger and you're subtracting, it would make the acceleration bigger, smaller, or the same size? Smaller. In fact, Quinn, there's a magic number when friction got so big that it exactly equaled 20, you wouldn't be able to move the bench anymore. A would be 0. Okay? Turn the page.
But then what happens when mu is equal to more than 1?
What happens when mu is equal to more than 1? It means if you were trying to move it, you would have to apply a very big applied force to overcome friction. Okay? And there's two issues here. First of all, friction is only as big as it needs to be. Let me give you an example. I'm going to make up a number. Let's suppose friction between this table and this floor is 30 newtons. That's the biggest it can be. If I pull with 8 newtons, friction is only 8 newtons. If I pull with 12 newtons, friction is only 12 newtons. How do I know this? It's not accelerating. If I pull with 29 newtons, friction is 29 newtons. As soon as I pull with 31 newtons, now I'm going to have a balance force. The reason friction can't be bigger than my pull is if I pulled with 8 newtons and friction was 12 newtons, which way would this table have to accelerate? Yeah, what you'd be able to do is you could tug on things and almost like a slingshot, they would go ricocheting off in the opposite direction. Is that what happens in the real world? So friction is a weird force, Jake, in that it's only as big as it needs to be until it reaches its maximum. What's its maximum? Mu times the normal force. Is that okay? And it's even weirder. You see, there's actually 2 types of friction. Now, I'm going to give you some homework that you can try right now. I'm going to spend like 10 minutes next class and also do the next lesson next class. Sorry. And I got a cool video to show you. But for now, you can try number 1, number 2. For all of these, I would probably be drawing a free body diagram. Number 3, number 4, number 5, number 6 is an algebraic question. I'll pause there for just a second.